Stoichiometry is the study of the quantitative relationships between the reactants and the products in a chemical reaction. We use stoichiometry to be able to determine what quantities of reactants we need for a given chemical reaction, as well as to predict how much product we can form in a chemical reaction. The amount of product that we can determine is the theoretical amount and does not take into account experimental error. Now, in general, just as a reminder, we can represent reactions with this kind of image as you see. When we do a representation like this, we are drawing molecules, and we are symbolizing a chemical reaction by considering that when we say 2H2 plus O2, we are talking about 2 molecules of hydrogen gas plus 1 molecule of oxygen gas that transforms and give 2 molecules of water. However, when we're doing calculations, we generally refer to quantities that are moles, not single molecules. That is because in a chemical reaction, there's a lot of molecules involved, and so making calculations with moles is far easier. In this lecture, we're going to use molecules to represent and understand the concepts, but for the calculations, we're going to use moles. For example, when we look at the reaction represented here of the decomposition of hydrogen peroxide to give oxygen and water, we can simply count the number of molecules that react to fill in those stoichiometric coefficients. And we can see that the balanced chemical reaction will be given by 2 molecules of hydrogen peroxide to give 1 molecule of oxygen and 2 molecules of water. The same reasoning can be used, and the same equation can be used to represent a reaction with more molecules or more moles. Now, when we do this, we can notice that if we divide all the coefficients that we obtain in this reaction by 3, we can obtain the original chemical equation, which is the one written with the smallest coefficients. And these substantially let us know that when we have a chemical reaction, we can use the ratio of the coefficients that we see to represent any number of moles that do react. Let's look at an example on how to use the number of moles that appear in the chemical equation to calculate reactant quantities and product quantities. In the reaction of carbon monoxide with oxygen to produce carbon monoxide, 2 moles of carbon monoxide combine with 1 mole of oxygen to produce 2 moles of carbon dioxide. We can represent this reaction in a table format, as you can see, by listing all the chemicals that appear without the stoichiometric coefficients and reporting the coefficients in a separate line. Let's assume that we want to determine when 16 moles of carbon monoxide are reacted, how many moles of carbon dioxide can be produced and how many moles of oxygen are needed. In this case, we will place the moles of carbon monoxide, 16, in the first row, where in correspondence with the moles. In order to obtain the moles of carbon dioxide, what we will do is divide by the coefficient relative to the carbon monoxide, so 2, divide by 2, and then multiply while coming up by the coefficient that appears under carbon dioxide. So 16 divided by 2 is 8, multiplied by 2 is 16. We can also calculate the number of moles of oxygen needed for the reaction by using the same method. So divide the 16 moles of carbon monoxide by 2 and then multiply by 1 and we obtain 8. Let's just look at an example on how to build this table. So how many mole of HBr will form when 0.327 mole of sodium bromide react with phosphoric acid? I'm going to pass to my notepad to solve this problem. So I have my reaction written here, and I have my data. Now, what I'm going to do to build the table, I'm going to first write my chemicals that appear in the reaction without the stoichiometric coefficients. Then I'm going to place a line with the coefficients, and I'm going to place the coefficients 3, 1, 1, 3 on this line. At this point, I'm ready to fill my data, which is 0.327. And while I'm doing this, what I need to do now is calculate the number of moles of HBr. So what I'm going to do, I'm going to divide the moles, 0.327 divided by 3, and then in order to fill the line of the HBr moles, I'm going to multiply by 3, and I'm going to obtain 0.327. With this method, I can also quickly calculate how many moles of H3PO4 are needed for this reaction if I want to. And all I have to do is take my 0.327 and divide it by 3 and then multiply it by 1. And I can get 0.109 moles of H3PO4 needed for this reaction. In general, when we are dealing with reactions in the lab, we don't deal with moles, but we deal with masses. Now, we can calculate masses from moles from masses by using the formula mole equal the mass divided by the molar mass. The general idea is that while the stoichiometric coefficients do not provide with relationship between the masses, but only between the moles, we can convert masses into moles, then convert moles of one chemical into moles of another chemicals by using the stoichiometric coefficients, and then convert back into masses. Let us look at an example where we can calculate the number of moles of CO2 that are formed when 112 grams of CO are allowed to react. We can also calculate the mass of CO2 that is produced when this mass of CO is reacted. Let's see how. The first thing we're going to do is set up our table to where we list our chemicals, we fill in the coefficient line, and then we add 2 rows, one for the masses and one for the molar masses. The molar masses are known from the periodic table, so we can fill those data in right away. The mass in grams is what is given to us in the problem, and that is the 112 grams for CO. So we're going to fill that in the corresponding line. Now, in order to calculate the moles of CO that we need for this reaction, we're going to divide the line of the grams by the molar mass. So 112 divided by 28.01. Do remember that when we're using this table, we're always dividing when we're moving downward and we're multiplying when we're moving upwards. So we obtain 4 moles. In order to obtain the moles of the CO2, we now want to divide the moles of CO4, divide by 2, and then multiply by 2, and we obtain 4 moles for CO2. At this point, if we want to obtain the mass of CO2 produced, we can easily do that by multiplying the moles by the molar mass and obtain 176. Now, we can also obtain the mass of oxygen needed for the reaction by using the same technique. Let us look at an example on how to use this method. So how many grams of ammonia can be produced by the reaction of 14.75 grams of N2, and how many grams of H2 are needed for this reaction? I'm now going to pass to my notepad where I have already my reaction written. So we have N2 plus 3H2, 2NH3. Our data is 14.75 grams of N2, and we want to know how many grams of ammonia are produced, how many grams of hydrogen are needed. So the first thing I'm going to do, I'm going to set up my table with my chemical species, and then I'm going to set up a coefficient line where I'm going to report my 1, 3, and 2, which are my coefficients. Once I have my coefficients written, I can start filling in the molar masses. And then these are going to be in gram per mole. And the molar mass for N2 is 28.02, H2 is 2.02, and NH3 is 17.03. And I'm going to use these in 4 6 figs, so they're all very consistent in terms of 6 figs. Now I know that my data tells me that I have 14.75 grams of N2. So my line for the mass in grams is the first line. I'm going to place this here. It is very important that you fill in the rows in the exact order. So mass, molar mass, moles, and coefficients. At this point, I can easily calculate the moles of N2 by simply moving downward and dividing 14.75 divided by 28.02, which gives me 0.5264. To obtain, I multiply 1 and multiply by the corresponding coefficient. So I can do this. So 0.264 divided by 1 multiplied by 3, and then I have 0.5264 divided by 1 and multiplied by 2. And so I get 1.053. And at this point, I can easily obtain the masses here as simply multiplying by moving upward the moles by the molar mass. So I'm obtaining 1.579 times 2.020 is 3.190. And then 1.053 multiplied by 17.03 is 17.93.